In this video, we are going to discuss acidity of carboxylic acids and the effect of substituents on the acidity of carboxylic acids. Now, as we all know, carboxylic acids have the general functional group RC-double-bond-O-OH. Now, this carboxylic acid can give away this proton and it can form ion, carboxylate ion, RCOO minus and H plus. Now, those who can give away proton, those who can donate a proton are acids. So, carboxylic acids are acidic. Now, the carboxylate ion formed by this dissociation is actually very stable because it is stabilized by resonance. How? Let's see. Now, look at this. This is a carboxylate ion where you can see there is a double bond between carbon and oxygen, and this oxygen carries an electron pair, negative charge. Now, let's see what happens if these two electrons come here. Then carbon and oxygen can form a double bond here. In turn, this pi bond will be broken and electrons will be shifted to this oxygen, making it negatively charged. So, what we will get are CO minus double bond O. Now, as you can see, the double bond can be equally shared between both the oxygens and this carbon atom. Actually, the carboxylate ion exists as a resonance hybrid, means it looks somewhat like this, RCOO, and the minus charge is actually carried by both the oxygens equally. This resonance hybrid therefore is a very stable ion and it makes the carboxylic acids considerably acidic in nature. But that being said, carboxylic acids are not strong acids. Strong acids like HCl, H2SO4, as soon as we put them in the solvent or aqueous medium, they dissociate all their molecules and they release the H plus ions or protons. But carboxylic acids are weak acids, they are not strong acids. Then how can we decide the relative strength of these acids? For weak acids, let us write the dissociation equation. Now, this is RC-double-bond-OOH, which is our carboxylic acids, and when we put it in water, it gives away the carboxylate ion RCOO minus plus H plus combines with the H2O to give H3O plus. So, this is the dissociation equation. Now, as per the law of mass action, if we write the acid dissociation constant for the dissociation of this weak acid, we may get Ka, which is the acid dissociation constant, or in this case, we can also call it acidity constant, and we can write it like RCOO minus the concentration of carboxylate ions into the concentration of H plus ions, means hydronium ions, because H plus ions do not exist on their own. They are always associated with water whenever they are in aqueous medium, and divided by the concentration of undissociated acid. This is the classic example of how we can apply the law of mass action to write the acidity constants for carboxylic acids. Now, when we write this, we can understand that the concentration of H plus ions produced is directly proportional to this acidity constant, means to this value of Ka. Now, as acids have more value of Ka or higher value of Ka, the acid strength of that acid is going to be increased. Means I will write two acids. First one with a Ka of say 1.3 into 10 raised to minus 2, and the second one with Ka 1.3 into 10 raised to minus 4. Now, as you can clearly see, this one has higher Ka than that acid. So, this acid is going to be stronger. So, higher the Ka, stronger is the acid. But you can see now I have just taken these values for example, they are not actual values. But I want you to understand that it is difficult to work with Ka values because they are very small. So, in practice, what we do is we use pKa values. Now, what is pKa? It is negative log of Ka. So, when we take negative logs of Ka, for example, for this acid, I have not calculated, but just for the sake of example, the pKa value may come 2, and for this, the pKa value may come around 4. Now as you can see, this Ka value was higher, but when it was converted to the negative log, the value became smaller. That is the reason smaller the pKa, stronger is the acid. So here very important to note that higher the Ka, stronger is the acid, but lower the pKa, stronger is the acid strength. So as we discuss this, I think we have got a fair idea of carboxylic acids, their acidity, why they are acidic, how they lose their proton, how the carboxylate ion acquires stability through resonance, what is the acidity constant which governs the dissociation of carboxylic acids, and we have also discussed the value of Ka and pKa, how they can be used to interpret the strength of acids. Now moving ahead, let us now discuss what is the effect of substituents on the acidity of carboxylic acids. Basically, the acidity of carboxylic acid is determined by the substituents placed on the alpha carbon of carboxylic acid. Let's understand. Now this is, let's take an example, CH3COOH. This is our acetic acid. Now you know this is the carboxylic acid group, which is composed of carbonyl group and hydroxyl group. This carbon is referred as carbonyl carbon, and the carbon next to it is always referred as alpha carbon. Now if you put certain substituents on the alpha carbon, it may affect the acidity of that acids, and this is totally attributed to the inductive effect. Now you might be knowing that the inductive effect occurs because of the polarity in the bond, and there are two types of inductive effects. If a certain group, see, I will write an example. Suppose there is a carbon oxygen bond, and here oxygen is more electronegative than carbon. So the groups which are highly electronegative like halogens, oxygen, hydroxyl group, cyano group, all of them have a tendency of withdrawing or attracting the shared pair of electron towards them. So what they do is they acquire the negative charge, partial negative charge, whenever they are in a system or in a bond, in a covalent setup. And these groups are said to exert negative inductive effect on the entire covalent setup. While there are certain groups like alkyl groups, then these alkyl groups have the tendency to actually push the electrons away from them towards the next atom. So in this case, this methyl group will push the shared pair of electrons towards the next carbon. This group will push the electrons towards the next atom. So these groups have the tendency to acquire partial positive charge, and so they are said to have positive inductive effect. Now this inductive effect is going to play the major role in deciding the acidity of acids whenever they are substituted. So now let's quickly see what happens when we actually substitute these acids. So let's take an example of CH3COOH. Now this is acetic acid. Okay. Before acetic acid, let's take an example of formic acid so that you will understand how the inductive effect actually works. This is formic acid, or in IUPAC we can say methanoic acid. Now let's take an example of acetic acid, which we will call in IUPAC ethanoic acid, and then let's take an example of propionic acid, or in IUPAC we will call it as propanoic acid. I hope you understand the nomenclature. If not, I will link the IUPAC nomenclature playlist here somewhere. You go through it, and actually you have to prepare the IUPAC nomenclature very well for the sake of organic chemistry. Okay, now let's come back to the topic. Now here you can see we are discussing the effect of substituent. Now here there is hydrogen, here there is methyl group, and here there is ethyl group. Now the size of alkyl group is going on increasing. Methyl is bigger than hydrogen and ethyl is bigger than methyl. So now what is going to happen to the acidity? For that you have to first understand that acidity depends on how easily the proton can be donated. What we are saying, an acid, it is a proton donor. So if an acid is able to donate the proton very easily, then that acid is a strong acid. But if that acid struggles to give away the proton, the acid may be a weaker one. Okay, so while deciding strength, we always have to consider this criteria. Whatever helps the acid lose its proton easily is going to increase the acidity, and whatever is going to make it difficult for the acid to lose the proton, it is going to decrease the acidity. Now let us come back to this example. As we know, the formic acid will have a certain acidity. I will tell you what is the pKa value for the formic acid. The formic acid has the pKa of 3.75. So let's consider the pKa for formic acid is 3.75. Now, whenever a methyl group is attached on the alpha carbon, then what happens? This methyl group exerts the positive inductive effect because alkyl groups are electron releasing. They actually push their electrons away from them. So what they do? Actually, they push their electrons towards this carboxylate ion. Now, the carboxylate ion is anyway going to be negative when the proton is lost. So, anything which can help to balance the negative charge on carboxylate ion will be stabilizing the ion and in turn increasing the acidity of ion. But if certain groups are going to increase the negative charge on carboxylate ion, then the ion will be destabilized and the acidity is going to decrease. So exactly that is happening here. This methyl group actually pushes its electrons towards the carboxylate part, making the negative charge more, and it makes the release of proton difficult. And release of proton is difficult means the acid strength is going to drop, and that is the reason acetic acid is less acidic or less strong than your formic acid, and this can be confirmed from the pKa value. The pKa value for acetic acid is 4.76. Now remember 2 minutes back what we discussed is lower the pKa, stronger the acid. So here you can see formic acid has a lower pKa, so formic acid is stronger than acetic acid. Now moving ahead, when we are going to increase the size of alkyl group, as you can see in this case, as the size of alkyl group increases, the positive inductive effect also increases, thereby pushing all their electrons towards the carboxylate part, thereby increasing the negative charge on carboxylate ion and thereby making the release of proton even more difficult. And so the acidity also drops in this case. So what, and we can confirm it from pKa, the pKa value is 4.87. As you can see, acetic acid is having a lesser pKa value, means it is stronger than your propanoic acid. So this is how we are going to actually interpret the acidity of carboxylic acids whenever electron releasing groups are attached. So we can safely say that the electron releasing groups can decrease the acidity of carboxylic acids, and as the positive inductive effect goes on increasing, the acidity goes on decreasing. As in this case, when the size of alkyl group increases, even when we go from primary to secondary to tertiary, the positive inductive effect is going to increase. In that case, the acidity going to decrease because they increase the electron density on carboxylate ion, making the release of proton difficult, and so the acidity goes on decreasing. Now let us study what will happen when electron withdrawing groups, the negative inductive effect exerting groups, are attached on alpha carbon. Let us take an example of acetic acid, CH3COOH. Now you know this is the carbonyl carbon and this is going to be our alpha carbon. I am going to substitute the alpha carbon with halogens. First, let us substitute one of the hydrogen with iodine, which is a halogen. Then let's substitute it with bromine. Then let's substitute it with chlorine, and then let us go and substitute it with fluorine. So as you can see, I have substituted the alpha carbon with halogen atoms. Now as I told you, halogen atoms exert negative inductive effect, means they actually withdraw the electrons from the covalent setup. They actually pull the electrons towards them. So what happens? Here acetic acid will have a particular pKa. Now let's compare the acidities with acetic acid. Whenever I replace one hydrogen of alpha carbon with iodine, iodine being negatively inductive, it will pull the electron towards itself, in turn reducing the negative charge on carboxylate ion. Now whatever reduces the negative charge, whatever stabilizes this anion, is going to help release this proton easily, and as the proton release is easier, the acid strength is going to be higher. So acetic acid and iodoacetic acid, obviously the iodoacetic acid will be more stronger. Now let's move on to bromoacetic acid. Now what happens? Iodine and bromine, when we look at them, bromine is more electronegative than iodine. So it will have even higher negative inductive effect. So it will pull the electrons even more strongly, in turn reducing the negative charge even more efficiently and making the release of proton even more easier. And so bromoacetic acid will be even highly acidic than your iodoacetic acid. Same applies to chloro. Now chlorine has even higher negative inductive effect than bromine, because chlorine is having higher electronegativity than bromine. So because of the negative inductive effect, the chloroacetic acid will be more strong or more acidic than the bromo, and the fluoroacetic acid is going to be the strongest of all, because fluorine we know is the most electronegative element in the entire periodic table, and that is going to exert the negative inductive effect very strongly, thereby making the negative charge stable and release of proton easier. So fluoroacetic acid will be highly acidic. Now as we compare the values of pKa also, we can see that the values actually fall like this: 3.18 for iodo, for bromo 2.9, for chloro it is 2.8 something, and for fluoro it is 2.59. So pKa values are going on decreasing, means the acid strength is going to increase, right? So here we have seen that when we actually substitute the acid with different halogens having different negative inductive effect, what happens? Now let's see. We will keep the halogen same and we will increase the number of halogen atoms. Let's take an example. This is our acetic acid. I will keep the acetic acid same. The pKa is 4.76. Now what I will do? I will actually replace one of the hydrogens with a chlorine atom, chloroacetic acid. Then I will replace both hydrogens with chlorine atom, and then I will replace all the hydrogens with chlorine atom. So what we can see here, this is acetic acid, this is chloroacetic acid, this is dichloroacetic acid, and this is trichloroacetic acid. So we have increased the number of halogens which have the electron withdrawing effect, negative inductive effect. So obviously this compound is not having any element with negative inductive effect, so it will have a certain acidity. But when we introduce a halogen which have the negative inductive effect, it will pull the electron density towards it, making the negative charge less prominent, hence making the release of proton easy. So this is going to be highly acidic than acetic acid. Now as there are two chlorine atoms, both of them will actually pull the electrons towards them, so it will be even more acidic. And in case of 3 chlorine atoms, it is going to be highly acidic. Trichloroacetic acid is highly acidic. You can see this from the values of pKa. The chloroacetic acid has the pKa of 2.86, dichloro 1.48 and trichloro 0.7. You can see the pKa is very small, the acid is going to be very strong. So this is how we can interpret when same halogen is repeated or the same group is repeated multiple times. Now one more condition we will study, ki if the group attached is away from the alpha carbon or near to the alpha carbon, that also will affect the acidity. Let's take an example. First I will take an example of butanoic acid. This is butanoic acid. Now what I will do, I will put chlorine on the 1, 2, 3, 4th carbon, chlorine. Then I will put it on the 3rd carbon, 1, 2, 3, and then I will put it on the alpha carbon, means 2nd carbon. So as you can see, this is our alpha carbon. The chlorine is put on the alpha carbon. Here it is placed on the beta carbon. Here it is placed on the gamma carbon. So we are actually moving the element away from the carboxylate ion part. So here, as it is closer to the carboxylate ion, the effect exerted by it, the negative inductive effect exerted by it will be stronger. So it will pull away the electrons, make the negative charge less prominent, release of proton more easier. So this is going to be a very strong acid as compared to this, because as the halogen is moved away from the alpha carbon, the effect decreases. As it is moved even farther, the effect even decreases. So in this case, the acid, this acid, alpha substituted acid, is going to be strongest than the non-substituted one, or this one, which is the gamma substituted version. So I think we have covered most of the conditions which can affect the acidity of carboxylic acids. Let us revise. See, carboxylic acids are acidic because they give away proton. Anything which makes the release of proton easier will increase their acidity, and anything which makes the release of proton difficult will decrease the acidity. Talking about the effect of substituents, initially we have seen groups like alkyl groups which are electron withdrawing, which exert positive inductive effect. They actually push their electrons towards the carboxylate ion, so making the negative charge prominent, destabilizing carboxylate ion, so it is difficult for them to release the proton. But in case of electron withdrawing groups which exert the negative inductive effect, they make the oxygen feel better by actually sharing the negative load of electrons, and so the release of proton is somewhat easier, so their acidic strength increases. Again, we have considered multiple cases where we have seen if we have different halogens with different inductive effects, what will happen? If we have same halogen but multiple times, what will happen? And if we have the same halogen but the position is far or near, then what will happen? I hope you have understood the concept of this particular part. This question is definitely being asked for 10 marks for your university exam of POC-I. So be prepared, and I hope this helps. If yes, don't forget to like and share this video with your friends who are studying the same topic. And let's meet in the next video. Till then, take care. Bye bye. Keep studying.